In this lesson, we'll be looking at what causes light to be given off by different elements under specific conditions. When lithium atoms are heated in a flame, their electrons absorb energy and move up to higher energy levels. Light is only produced when those excited electrons fall back down to lower energy levels. When they do, the atom releases energy as light of very specific wavelength. In the image, the mole is thermally exciting some lithium atoms. We can tell it's lithium because of this hot pink color in the flame. It's very characteristic for lithium. The emission spectrum over here on the right shows the discrete lines that you would observe if you looked at the flame through a spectroscope. So we have a really strong red line, which is where it gets most of its red color. We also have a fairly strong yellow line. By the end of the lesson, you should be able to determine the wavelength of a photon involved in an electronic transition, whether the photon is being absorbed or emitted, and rank the photons by relative energy level. In the Bohr model, electrons are assumed to move in very specific paths around the nucleus. However, Heisenberg said that the Bohr model didn't properly describe electron behavior due to the small size and high speed of the electrons. Heisenberg's uncertainty principle tells us that there is a fundamental limit to how closely we could describe either an electron's location or its energy or momentum. Those two are linked. As we get closer and closer to locating an electron, the uncertainty in its energy gets larger and larger. The scale of this uncertainty interval is set by Planck's constant, which tells us that the energy and position come in very small, discrete amounts. But there's more to the story. In quantum mechanics, making a measurement changes the system, which leads us directly to Schrödinger's cat, which is a thought experiment intended to illustrate the effect an observer has on a quantum state. So in Schrödinger's cat, we have a box, and the box, once it's sealed, you can't see anything inside of it, obviously. You can't hear anything, you can't smell anything. There is no way for you to observe what is going on inside of the box. Before you seal up the box, we're going to put a cap, and we are also going to put a piece of radioactive material. Now, this radioactive material has the property that there is a 50% chance that it will give off a radioactive particle every hour. If it does give off a particle, the Geiger counter right here will detect it, causing it to release the hammer, which then swings down and smashes a vial of poisonous gas, which then kills the cat. So we seal up the box, wait for an hour, and then after that hour, as long as we don't open up that box, there's a 50% chance that the cat is still alive, which is what this picture is supposed to be showing, or there's a 50% chance that the cat is now dead. As long as you don't actually observe it, the cat exists in a superposition of states. This does not mean that human consciousness magically controls reality. Instead, it means that any interaction that gathers information, light hitting an object, a detector clicking, a measurement being made, forces the system into a single observable state. So in this next bit, we have a video which kind of goes over some of the weird behavior of electrons and how they also display this quantum behavior.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter, through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. It was here that physicists stepped forever into the strange, never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
All right, so I've shown that video for years, and I've had some funny results. People have said, oh man, that made my brain hurt. So in the next part, we're going to be looking at a diagram that is in your reference packet. I have edited it just a bit so that I could get the transitions, which is shown with all of these circles up here, and the colors that go with the visible light spectrum part of it in the same place. Otherwise, it was just too long. So here we see the Bohr model of the hydrogen atom. So we have the dark circle in the middle is the nucleus, and then we have the different energy levels. They did a pretty good job of getting them drawn properly. So there's n equals 1, n equals 2, 3, 4, 5, and 6. You can see we have a whole bunch of arrows going between the different rings. These correspond to the electron transitions. So if you're going between the first energy level and anything else, all of those wavelengths end up down in the ultraviolet region. If you're going between the second energy level and anything out farther, then you end up in the visible light part of the spectrum. And then if you are looking at going between the third energy level and farther out, then that would be the infrared region. Now remember, we have even more electromagnetic bands past infrared. So if we were to go between the fourth and anything else, that would be out in radio waves, I believe. All right, so let's look at these guys right here. So notice that we have, for the visible light spectrum, because that's the one that's easiest to visualize because you can actually see the colors that are being given off if you have the transition going in the right direction. Notice that the arrows are drawn so that they're going from a high energy level to a lower energy level. So something I want you to remember is that when you're going from high to low, that's where you're going to get the light being given off. The photons are being emitted. So here is the hydrogen emission spectrum. And notice we got 1, 2, 3, 4 lines. And here we have 1, 2, 3, 4 possible transitions in the visible light spectrum. So remembering that the longer the wavelength, the more towards red it's going to be. So we can say, all right, well, 656 is going to be this one. We're going between 2 and 3. That's the lowest energy photon. That one corresponds to this red photon that's being generated down here. And then, whoops, I did it the other way around. So if you go to shortest wavelength, highest energy, that's towards the violet end. So this is between 6 and 2. So that would be this violet guy down here at the end. The next one I didn't do because it was too hard to fit in there, but that would be 434. This teal colored one would be the n equals 4 to n equals 2 transition. And then the last one, as I just said, because I got myself backwards, is the n equals 3 to n equals 2. Now these are all emissions. They're all going from a high energy level to a low energy level. Now if we're going the other way, it can go the other way. They just chose to have it illustrated for just the emission lines. That means that if you go from low to high, so small numbers to higher energy numbers, that means you are exciting the electron and the photon is being absorbed. So here we have the absorption spectrum for hydrogen. And so we have a continuous spectrum in the background, and you have these black lines where that specific wavelength is being absorbed by the electron. So the first black line down here at 410 would be the n equals 2 to n equals 6. We're going up because we're absorbing the energy. And then the band that's in between blue and the teal color is the going from n equals 2 to n equals 4. And then the red one will be n equals 2 to n equals 3. So remember, high to low makes it glow. You have light being given off. Low to high, that means you are exciting an electron, so it's going to be, you're not going to get any light being given off. It's being absorbed. All right, so now let's use this diagram in order to answer some questions. So it says, which electronic transition results in the emission of the lowest energy photon in the ultraviolet region? So this is kind of like a two-part question. So it says we're in the ultraviolet, and it wants the lowest energy photon. So you have to remember that as wavelength goes down, frequency goes up, and energy goes up. So we want the lowest energy, so we want the longest wavelength in the UV. So here's UV, longest wavelength would be 122. You trace it back, and it's going between n equals 2 and n equals 1. It says it wants emission, so we're doing high to low. So it would look like that. Which electronic transition will absorb the highest frequency infrared photon? So frequency is inversely proportional to wavelength. So if we want the highest frequency, we want the shortest wavelength in the IR. So shortest wavelength in IR is 1094. So it's going from n equals 6 to n equals 3. Whoops, I had it backwards. It was absorb. So that means it's going from low to high. Which electronic transition shown emits, so we're going from high to low, a photon with the longest wavelength. Okay, so our longest wavelength is going to be way over here, over in the IR. It's 1875. And so we trace it back, and it's going between, and it's emitting, so 4 to 3. And then we got a follow-up question on that. Which part of the electromagnetic spectrum does the photon from number 3 fall? So you can say, well, it's IR, but we can get a little bit more information on that. So we come down here, we can see where at the long end of the spectrum of the IR band, it overlaps with microwaves. So that one could either be in just infrared or could also be in microwaves. All right, so we got a few more questions. So we want to compare the energy of a photon emitted, so given off, during a 3 to 2 transition to one emitted during an n 6 to 1 transition. Which photon has the higher energy, and how can you tell from the diagram? So, well, there's a couple of ways you can do this. I kind of looked at where they were ending up. So remember, if it ends in an n equals 2, it is a visible light emission. And then if it ends up in an n equals 1, it's a UV. UV wavelengths are shorter than visible light. So therefore, the photon with the higher energy would be the n equals 6 to n equals 1. And then we want to rank the following photons from lowest energy to highest energy. So we have UV, IR, and Vis. So just looking up here, we see as the wavelength gets shorter and shorter, the energy is going up. So here's a little diagram, and I've got the colors. I tried to line it up. So longest wavelength has the lowest E, shortest wavelength has the highest energy. So you just say, all right, well, the longest wavelength is IR. So that's going to be the first one. Visible is in the middle. And then UV, out of those three, has the shortest wavelength. All right, so that's it for this lesson. It's a real short one. It's all on just how to read that diagram. So wrap up. Electrons absorb energy, and they move from low to high energy levels. That's where you have excitation or absorption of a photon. Electrons emit photons when they go from high to low. Remember, high to low makes it glow. And that's where you have emission. Each electron transition produces or absorbs a photon with a very specific wavelength. So 656 is going to be the red one. 1875 is that really long one down in IR. Shorter wavelength means higher frequency, which means higher energy across the entire electromagnetic spectrum. And then you can use atomic spectra, the light that is being given off, to identify elements, because it is unique for the elements, because they all have their own energy levels, and they have their the electrons are going to be interacting with each other, especially once you get past hydrogen. So they are unique. And we're going to be doing a flame test shortly, where we're going to be identifying some elements based on their flame colors. All right, so that's it for this lesson. Thanks for listening.